Okay, I think we are ready to start. Are there any questions before we start? So please wait after the class. I will hand out the graded exams and the next week's homework is already posted, so you should be able to see that. And I'm going to start next topic today, scaling and round-off noise from chapter 11 of the textbook. Scaling and round-off noise. A lot of DSP books nowadays don't really teach a lot about scaling and round-off noise, particularly for the state space representation. So that is the main focus of the chapter, and we will look at that. Okay, are there any questions before we start on this new topic? Okay, the scaling and round-off noise is a very important part. I mean, long ago when programmable DSPs came out, and I'm talking about 1980s, late 1980s, somebody would program a 256 tap FIR filter, and the output of the programmable DSP would be all garbage. And that's because the programmer did not consider scaling or round-off noise properties of these implementations. So before we start scaling and round-off noise, we are primarily interested in fixed point implementations of DSP systems, and these are represented using so-called 2's complement arithmetic. And so we can assume a typical representation in 2's complement arithmetic with range, dynamic range between -1 to 1 would be, for example, 0.1011. So this is called the sign bit, which is a 0, means 0, and then these bits are weighted bits, 2 to power -1, 2 to power -2, etc. So the arithmetic value of this would be 2 to power -1 plus 2 to power -3 plus 2 to power -4, and that is half plus an eighth plus 1/16, and half is 8 plus 2 plus 1, 11 by 16. Okay, so that is that number. And if this was 1.1011, and this 1 again is a sign bit, which means if this is 1, the arithmetic value is -1. Plus the weighted bits are the same, 2 to power -1, 2 to power -2, etc. And then this is -1 plus 11 by 16, which would be -5 over 16. So that sign bit, if it is 0, then that's a positive number unless these are all zeros, in which case that's 0. And if the sign bit is 1, that is a negative number. So that sign bit is 1, then you know that's a negative number. Okay, so there are two kinds of approaches to reducing the number of bits. So if I have let's say I have a number 0.1010111, okay, something like that, and let's say that I want to reduce that to a word length of, so if I want to reduce this or represent this, so what happens when we do a multiply add? So we multiply a number and add something to that. Ultimately, so if we, for example, if we start with a 10-bit data path and let's say a well, let's 8-bit coefficient, the product of 10 bit and 8 bit, it's like a convolution, right? So the convolution of a 10-point sequence with 8-point sequence is of length 10 plus 8 minus 1, and the multiplication in many ways is kind of a convolution in another domain. So this would be 17 bits, and let's say this was also 10 bits, then this would be 17 plus 1, it could be one more bit, 18 bit. And we may be interested in reducing that, somehow quantize that to 10 bits, because we may be interested in maintaining a so-called fixed width in the whole system. So the signal word length may be 10 bits everywhere. So when the multiply add computes, it computes the complete result, which in this case is 18 bits, and then we represent that using 10 bits by some kind of approximation. So there are two ways of approximation. One is simply called truncation. So when we truncate, throw out everything after, so in this case 1, 2, 3, 4, 5, 6. So if you truncate to 6 bits, and this would be 0.10101. So throw away everything after 6 bits. Now another approach to approximating that is called rounding. So when we round a number, and then we just don't throw away all the bits after 6 bits, which is the word length that I want to approximate to. So the thing to do for rounding is you look at the bit after the 6th bit, look at the 7th bit. And if that is a 1, then add a 1 to the LSB. And if that's a 0, well then do nothing. You can add a 0, but adding a 0 doesn't do anything. And so if I do add that 1, so I get 1 plus 1, 0, carry 1, 1 plus 0, 1. So that's the number I get. So if I round that, then we get 0.10110. Okay, so if we look at what this number was, this was half plus 8th plus 16th plus 32, 32nd. Okay, so okay, oh no, one more one here. Okay, there is one more one, so we shouldn't ignore that. Okay, so plus 1 by 64. Okay, so that's 32 plus 8, 40, 44, 46, 47 by 64. Okay, and if you look at this quantity here, and that is half plus 1/8. Something doesn't seem right. Half, quarter, 8. There is no 1/8 here. Yeah, there is no 1/8. 32, 64, 128. Okay. Yeah. So then this would be 64 plus 16. That's 80, 84, 86, 87. Okay, so that's 87 by 128. Okay. Okay, so 87 by 128, and this one is basically we truncated that, we threw out everything after 30 seconds, so these two are gone, these two are gone. So we have 16 plus 4, 20 plus 1, 21 by 32, okay, which is 84 by 32. So the error here is going to be minus 3 over 128. Okay, so 84 by 128 minus 87 by 128, so which is minus 3 by 128, the final value minus the initial value, and in this case this number is going to be slightly more than that, so that's going to be half plus 8th plus 16th which is 88 by 128, 88. So error is going to be 1 over 128. Okay, so the maximum error by truncation is always going to be 2 times the maximum error by rounding. So rounding always is going to have a less amount of error than truncation. So let's talk about the maximum error. E max is maximum absolute error. So we don't care about minus or plus, we take the absolute error. And E max with rounding is going to be half of E max with truncate. Okay, so that's why a lot of the multiply accumulators that do multiplication followed by add operation usually will round the result at the end, so they will look at the next bit position. If that is a 0, then do nothing. If it is a 1, then add a 1 to the LSB of the W bit number, and then you get a slightly different result, which as compared to truncation, which minimizes the error. So it may be useful to think about the same number here. If I just made both of these numbers negative by just having a 1 at the sign bit, okay, then it may be a slightly different observation, but the absolute error won't change. Absolute observation will still the same, and this is what I wrote down here is correct with respect to the absolute error. Okay, so let's see what might be. So if I have a number 0.10010, let's say, and then we have many things here. Okay, we have many things here. So let's say this is W bit. Okay, this is W bits, and then this is the weight of this is 2 to the power minus 1, 2 to the power minus 2. How many bits? This is called an integer bit. The sign bit is called an integer bit, and these are called fractional bits. Or sometimes called decimal bits. And then what is the weight of this one? So that's going to be 2 to the power minus W minus 1, right? Because, so in this example, if W is 6, there are 6 bits, 1 is sign bit, 5 bits are fractional bits. The weight of this one is 2 to the power minus 5. 2 to the power minus 1, 2, 3, 4, 5. Now, what is going to be the maximum possible error for truncation? Maximum error occurs for truncation when will the error be maximum? That is when all of these are 1, 1, 1, 1, 1 all the way to infinity. So if you think about if all bits after W bits are 1, and that's when the error is maximum because we threw out all of these. And that maximum error, E max, is going to be, so this is 2 to the power minus W plus 2 to the power minus w plus 1 plus 2 to the power minus w plus 2 up to infinity. So if there were a word like, well, okay, approaching infinity, if there was a very long word and all the bits were 1 after these w bits, then the error is going to be maximum, and this is 2 to the power minus w taken outside a bracket, 1 plus a half plus quarter up to infinity. And if you apply the formula A by 1 minus R, this is a geometric series. A is 1 by 1 minus R is half. Okay, 1 minus half is half. 1 by half is 2. So that is going to be 2 times 2 to the power minus, 2 to the power 1, 2 to the power minus w minus 1. Okay, so that is going to be the maximum error, and we can call that delta. We can call that quantity delta. Okay, so that is going to be the maximum error with truncation, maximum error for truncation. And the maximum error with rounding, okay, this is truncate, and I won't go through, but you can check. Will be delta by 2, so it will be half of the maximum error with truncation. By rounding, the maximum error is going to be half of the maximum error with truncation. So if w was 6, as in this example we were working out, w is equal to 6, w minus 1 is 5, 2 to the power minus 5 is 1 by 32, so the maximum error with truncation would be 1 by 32. So you can see 1 by 32 is 4 by 128, and this error absolute value is 3 by 128, which is not maximum yet. It's not maximum yet, because if it were to be maximum, then we would need all these ones all the way up to infinity. Think about a 500-bit number or 100-bit number with all ones going on. And the truncation would be 1 by 64, which would be 2 by, rounding would be half of that, which would be 2 over 128, and that's less than that. So this is 1 over 128, which is less than the maximum. And so, those are concepts of scale, truncation and rounding. We are interested in understanding how to scale signals so that the scaling will guarantee the output range is limited to something between minus 1 to 1. So if we have a number, some sign bit, for example, so this is this kind of number is always limited to minus 1, 1. So the minus 1 means 1 point, all zeros. And this one is open bracket, means we can never realize exactly 1, because if we have 0.1111 etc., then it will be still, if a number like this will still be, so this is w is equal to 8, right? So 3 plus 3 is 6 plus 2 8, and this is going to be 1, so the number is going to be 1 minus 2 to the power minus 7. Okay, so that is the maximum number. So if you at 0.11, which is 3/4, that's 1 minus 1 by 2, 1 minus 1 by 4, and that 4 is 2 to the power minus 2. And that 2, this 2 is the same weight as this 2. So same way here, this weight 2 to the power minus 7, same as 2 to the power minus 7 here. So that's why it is open bracket. So it doesn't make sense when we are realizing in hardware multiplying by something by 1, but we are not representing that. But that's not really what circuits do, right? When the coefficient is 1, you have a bypass, right? So when the coefficient is exactly 1, then you bypass the multiplier, don't multiply anything. And so that's essentially a bypass operation. So if we have, so you have a check, you check if the coefficient is 1. So you have a select signal, and let's say that this is coefficient is 1. Then you take the result of the multiplication. So if we were computing W times or W times X, and if this is X, then coefficient is 1. If this is true, if this is coefficient is equal to 1, so that's a logical signal. And if this is true, then you bypass, so the output is just X. And if it is not true, then you take the value of that product. Okay, so that's why we don't really multiply anything. If the coefficient is 1, we just bypass the multiplier. Okay, so so sometimes we may be interested in more integer bits. So for example, if I have something like that, so this then is the sign bit, but then there are more integer bits. Okay, I say integer because these are fractional bits. So a value of a number like this would be 2 to the power minus 1, 2 to the power minus 3, and this is going to be 2 to the power 0, which is 1, and this is 2 to the power 1, which is 2, and this is going to be 2 to the power 2, which is 4. But in this case, the sign is 0, so this number is going to be 3.4 by 8 plus 1 by 8, 5 by 8, 3 and 5/8. Okay. And if that number was 1, everything else was same, this would be minus 4 plus 3 plus 5 by 8. Okay, so that would be minus 1 plus 5/8, which is minus 3/8. And really having a lot of 1s in the integer bit is really not helping us. If the value of this is minus 1, we might as well just require one sign bit, and that's about it. So yeah, if all these bits are all 1s, then we really didn't need them, but this middle bit could have been 0, or that other bit could have been 0. So that's kind of general. Sometimes we might think about signals with a dynamic range more than 1. So I might say, okay, the dynamic range of the signal is minus 8 to 8. Minus 8 to 8. So then we will need 4 integer bits. Right, with three integer bits, I can represent between minus 4 to plus 4. Okay. Why minus 4? Because if this is 1, all others are 0, then that's minus 4. And something slightly less than 4 would be 3 point something, 4 minus epsilon or 4 minus delta, that would be 0, 1, 1 point, whatever is here, so that's 3 point something. If I want dynamic range between minus 8 to 8, then I need 4 bits. So the sign bit will have weight minus 8. So, so let's now talk about what is called L1 scaling and L2 scaling. And you may have come across some of these in the beginning DSP class, which is perfectly fine, and it's a good review anyway. So the whole idea of L1 scaling, if I have a signal input, so if I have signal input xn, and then we scale it down, we multiply it to something to get scaled signal xsn, and then it goes through that filter hn to get output yn. So the L1 scaling tries to make sure that the output yn is bounded by 1. The maximum of the output is that's L1 scaling. So we always guarantee that the absolute value of the output is bounded by 1. It's always lies between -1 to +1. So that's called L1 scaling, which is very restrictive. And so why is it restrictive? Well, maybe 95% of the time it's between -1 and 1, but 5% of the time it is more than 10 or more than 100. And then I have to scale down the signal so much in the beginning that now if it was already more than 100, that has to be scaled down to 1. And that really means I might lose a lot of the useful information of the signal. L2 scaling, on the other hand, tries to make sure in some sense mean squared value is less than 1, but in general the expected value of y squared n is less than 1. So that's L2 scaling. 2 means simply it's in the square sense, not the absolute value sense. And so that's the square sense, right? So that means if it's okay if the output goes more than 10 or 100 some of the time, as long as the expected value in the square sense is less than 1, then it is okay. So what might be the scaling for L1 scaling? How might I compute the scale constant here S? Okay, how might one compute that scale constant? So yn is equal to summed over xn, let's say summed over k hk xn minus k. So in a system with input xn output yn. So if let's assume that xn absolute value is equal to x max, okay, maximum of xn absolute value is x max. Okay, so yn, we want to make sure the absolute value of yn for all n is less than 1, because why do I say less than 1? It simply means one integer bit. There are no additional integer bits, just one integer bit, all others are fractional bits. We don't have more integer bits in the representation. So yn absolute value is going to be less than or equal to absolute value of hk xn minus k. Okay. Now any thoughts about why that is true? So this is this quantity here is sum of many numbers. So if this was a 100 tap filter, there would be 100 things. Okay, let's say that I'm just going to talk about two numbers. Let's say 5, so plus minus 3, or maybe even minus 15, let's say. So let's have three numbers. So k takes three values, and if I add these three, that is going to be minus 13. Minus 13. Now, if I add the absolute value of this, and that's going to be 23. Okay, so the absolute value of the sum, absolute value of the sum. Okay, let's put it this way here. Absolute value of the sum is going to be, okay, so yn absolute value is going to be absolute value, yn absolute value is going to be absolute value of that sum. This is absolute value of the sum, and that is always less than, absolute value of the sum is always less than or equal to the sum of the absolute value. So absolute value of the sum is always less than sum of the absolute value. Okay, so if we take the sum of the absolute value, so this absolute value of the sum, which is the left side, is equal to, less than or equal to sum of the absolute values. Okay. Now I have absolute value of a product. So absolute value of product, if I, for example, absolute value of 5 times minus 3, which is minus 15, is same as absolute value of 5 times absolute value of 3. So we can then say that this quantity here so yn absolute value is less than or equal to summed over all k absolute value of hk times absolute value of x and minus k, and that is less than or equal to summed over all k hk absolute value times x max, because we already know that this quantity here is always less than x max, the absolute value of that, which means that to guarantee that yn is bounded between minus 1 to 1, we can set this quantity is equal to 1, and that says that x max should be equal to 1, so this is equal to 1, so 1 by summed over all k hk magnitude. So that is going to be for yn magnitude to be less than 1 for all n, So if we want to make sure for all n the absolute value is 1, less than 1, then the maximum value here should be should satisfy this equation here. So to let's take an example. Let's say that we have a first order filter. Let's say 1 by 1 minus 0.3 z to power minus 1. Okay, so if this is the filter, h of z is equal to 1 over 1 minus 0.3 z to power minus 1 is equal to 1 by 1 minus x is equal to 1 plus x squared up to infinity. So that's the geometric series. So 1 plus 0.3 z to power minus 1 plus 0.3 squared z to power minus 2 plus 0.3 cubed z to power minus 3 up to infinity. So h, if you just compare this, h0 is 1, h1 is 0.3, h2 is 0.3 squared, h3 is 0.3 cubed. Okay, and these are all positive, so the absolute value is the same as itself, right? So sigma absolute value of hk is the same as sigma hk. Why? Why is that? Because hk is non-negative. Well, in this case it's positive. So hk is positive, so the absolute value is the same as itself. What is a very quick way to, I guess you could always say, okay, I can add 1 plus 0.3, all these things, and then take the geometric series, and then it brings you back to 1 over 1 minus 0.3. So, but a quick way, what I was going to say is a quick way, if hk is positive, then this quantity is simply h of z evaluated at z equal to 1. Okay, so that's that sum, because what is h of z by definition? Summed over all n, hn z to power minus n. If you substitute z equal to 1, so summed over all n hn. If these are all non-negative, then that's same as the absolute value, and that's going to be 10 over 7. Okay. So x max is going to be 1 by 10 by 7, which is 7 by 10. 7 by 10. So I need to guarantee that for this particular example, this signal should be bounded to 7/10, for example, for the output y to be bounded to 1 in magnitude. That's that quantity 1 by summed over all k, hk. And let's say that in some application I am working on, xn is bounded from minus 10 to plus 10. So let's say that xn is bounded between minus 10 to plus 10. Okay, so then what that means, I need to bring this dynamic range down to 7/10. Okay, so what will the scaling factor be? So that would be 7 by 10 divided by 10 or 7 by 100. So whatever is the signal, if it is 10, multiply by 7 by 100, then that is bounded between 7/10. Well, that's exactly 7/10. Okay, so that's kind of how we can compute the scale constant so that the output of the filter can be guaranteed to be between minus 1 to plus 1. So we want to spend, these are good examples to understand what the concept of scaling is, but we really want to spend time to understand how to compute scaling and round-off noise effects in digital filters using state space representation, and that's really what the main goal of this chapter is. So in order to understand that, we need to compute two types of matrices. So we will talk about two types of matrices, K and W, and this matrix is used for scaling, and this matrix is used for round-off noise. Okay, we will talk more about that. So let's start with a state space representation of a filter. Xn plus 1 is equal to a xn plus B UN. And Yn is equal to C transpose Xn plus D UN. So this Xn is n by 1 vector. This is a column vector of dimension n, which means that it has n states. The number of states in the digital filter is n. This is the state transition matrix n by n. U is a scalar input and the B is another column vector n by 1. This is n by 1. This is 1, just 1 by 1 scalar. And if this is n by 1, this is a row vector 1 by n. And both of these are scalar 1 by 1. Okay. Well, 1 or 1 by 1 doesn't really matter. So if we think about this as a signal flow graph, the signal flow graph representation can be shown like this. So the next state xn plus 1, so that's next state, and that is the current state xn plus 1, and this is a delay. Xn plus 1 is equal to A times that plus B times input U. Output is C transpose times Xn plus D times UN, and that is output Yn. Okay, so the idea of a scaling in the L2 sense, in the mean squared sense. So this is a vector of dimension n, column vector. So we want to make sure expected value of xi squared n is equal to 1 for all I equal to 1, 2 up to n. So if there are n states, we want to make sure that the mean squared value, by the way, we are making an assumption here that all these variables are zero mean. We are assuming that the input is zero mean and has variance sigma u squared. Okay, so the whole purpose of scaling is to make sure that after the filter is scaled, the expected value of each and every state after scaling, square of that will be 1. And so in the K matrix that I was talking about, we will define the K matrix. So in the K matrix, the so-called KII, the diagonal value of the K matrix, we will, this I'm just going ahead, but just mentioning that the diagonal value of that K matrix, we will see that it represents expected value of xi squared n. Okay, we will talk about that. And we will define what K is also. So K, so let's define K. So what is that K matrix? So this is n by 1, this is a row vector 1 by n. So K is n by n matrix. So this is expected value of a column vector x1, x2 up to xn times a row vector x1, x2 up to xn, and that is going to be equal to expected value of x1 squared n, x1n, x2n up to x1n, xnn x1 n, x2 n, x2 squared n, x2, x3, x2 and x3n, that's the end, x2, xn, and finally xn, x1 up to xn squared n. Okay. So if you now look at the diagonal elements, this expected value of x1 squared, there is this expected value here. Expected, so this is k11, k22, k33, and knn. And the whole purpose of scaling is after scaling, not before, after scaling, these diagonals should be 1. And that's the whole goal of scaling. And we will learn about how we can scale so that the diagonal values become 1. Okay, so we will talk about that. Any questions before we get to how to compute the K matrix? How do we compute K matrix? So to compute the K matrix, we need to express. So if I assume the input signal to be a zero mean random process with variance some sigma u squared, it doesn't really matter. So the only deterministic quantities are these state parameters A, B, C, D. This is zero mean random process, zero mean, and we can assume unit variance. It is okay to assume the variance is unity. So it's all right to assume sigma u squared is equal to 1. And then we want to compute K, right? So K matrix is defined as expected value of x transpose. So we need to compute an expression for xn so that I can compute the K matrix. And to compute the xn, what this is, so I need to think about the transfer function from the input to the state x. So just consider this part of the system, ignore the remaining part, ignore the output, ignore that edge. So if we were to compute what is an expression for xn in terms of un, I need to analyze this system with a feed-forward part B and this loop here with loop gain A times z to power minus 1. So, and then we can then substitute that to compute expected value of x so we can compute that quantity here. So once we have that xn, this is the x vector n, this is the vector xn, okay, so this is the vector. So this is the vector xn, and then the transpose, so I need to compute an expression for xn in terms of un. So compute xn in terms of un by transfer function analysis. Okay, so that's not really that hard, so we can compute xn using, so let's define f of z is equal to xz by uz, and that is equal to f1z up to fnz. Okay, so we are saying that the transfer function from u to x, the transfer function from u to x is going to be, So think about x is a state vector. So the transfer function from u to x1, this is a vector. I'm not really representing that here, but yeah, you should think of these as vectors. And then that is going to be a vector. This is a vector. So f1 is the transfer function from u to x1, u to x2, etc. Okay, so what exactly is that quantity? So this is going to be the forward gain, which is z to the power minus 1 times, if it was a scalar system, I would write that as 1 over 1 minus loop gain, which would be 1 over 1 minus a z to the power minus 1 for a scalar system. But because this is a matrix, we cannot write that, so I can write this as I, the identity matrix of dimension n, minus the matrix A times z to the power minus 1, inverse of that. Okay, this is n by n, this is also n by n. And so instead of having scalar expression like that, we take the inverse of that matrix multiplied by that quantity b, multiplied by b. Okay, so this is going to be equal to b z to the power minus 1 times, by the same formula, 1 minus x, 1 by 1 minus x is 1 plus x squared plus x cubed. That's the infinite geometric series. And so this is equal to b z to the power minus 1 plus ab. Well, I think I made a mistake. So b should be on the right hand side. This is n by n, that is n by 1. B cannot be pre-multiplied, the dimension should be wrong. Plus a squared b z to the power minus 3, etc. So which means if you think about fz, think about this as the z transform, which is f0 plus f1. So this is f0, this is f1, this is f2 and f3, etc. And that means the fn or fk, fn is equal to a to the power n minus 1 times b, n greater than or equal to 1, 0 otherwise. So f0, if you substitute f0, then it's 0 because it's otherwise. If you substitute, no, I made a mistake. This is f1. So f1 z to the power minus 1. So this is f0 plus f1 z to the power minus 1 plus f2 z to the power minus 2, etc. And that quantity is 0 because there is no constant term here. Okay, so f3. So f3 you can say 3 minus 1, a squared. So that is the vector fn. So now I can compute xn. So what exactly is xn? Xn is equal to un, the input convolved with fn. So if I know the impulse response fn or unit sample response fn from the input u to this point with output the state xn, then the output here, the state xn, is u times the impulse response from u to x, which is f. So then this can be written as summed over all k fk un minus k, and we substitute n equal to k, then we can get. So these are a little algebra, but you will see at the end when you do some MATLAB problems, you will see how to compute this K and W very quickly using MATLAB, using only a few lines. So Xn is equal to summed over all K, a to the power K minus 1b times Un minus K. Okay, so that is substituting Fk from that expression here. And then we can compute K, which is the expected value. K is the expected value of X times its transpose. So K is equal to expected value of X times its transpose, and that is going to be the expected value of this X is summed over all K, a to the power K minus 1b Un minus K, times the transpose of, so now I can take another index L, I take another index L, and then take the transpose of this. That A, B, C transpose is going to be C transpose, B transpose, A transpose. So this is going to be U n minus L, because U is a scalar, times B transpose times A to the power L minus 1 transpose. Okay. And then I can write that as expected value of the double sum K and L, a to the power K minus 1b times Un minus K, Un minus L times B transpose a to the power L minus 1 transpose. Okay, then the next, so double sum, and then take the expectation from outside the sum to inside the sum. Expected value of the sum is the sum of the expected value, and U is a random process such that it has zero mean and variance 1. So this quantity here is going to be 0 if K is not equal to L. If K is not equal to L, then Un minus K and Un minus L are, we can take the expected value of this times that is expected value of this times expected value of that, which are both zeros. And if K is equal to L, then that's just sigma U squared, and which I can just assume to be 1. It doesn't really matter. Okay. So then finally this whole double sum has a value that is non-zero when K is equal to L. Therefore I can just substitute only one summing index instead of both, and this is sigma U squared taken outside the bracket, outside the sum, a to the power K minus 1b, B transpose, K is same as L, so replace. Okay, so that is that's the K matrix. Okay, so so you could also write this as sigma U squared delta K minus L. Okay, that doesn't matter so much. Okay, so now, so for now I can assume sigma U squared to be 1, so it really doesn't matter. And so what happens if you look at this matrix K? So K matrix is defined by this in terms of A and B. So if I write this as K equal to 1, what do we get? B transpose. If K is equal to 2, we get A, B transpose, A transpose. If K is equal to 3, K equal to 3, 3 minus 1, 2, A squared B transpose, A squared transpose. K equal to 4, A cube, okay, A cube B transpose, A cube transpose. And so then, if you think about this, I can write this as BB transpose plus A taken outside a bracket on the left side, a transpose taken outside a bracket on the right side, and then this is going to be BB transpose. This is going to be A taken outside on the left, so A, B, B transpose. A transpose taken outside bracket here from A squared transpose. And you will quickly observe that this whole thing is nothing but the same K matrix. So K can be expressed in terms of itself by that equation that K is equal to B times B transpose plus A times K times A transpose. So that's the way that we can quickly compute K by MATLAB using few lines of code. Very quickly we can compute by an iterative process. So this has anybody come across this kind of equation in a control class or some other class? This is called the Lyapunov equation, right? I don't know if you have come across. So equation that looks like this is called Lyapunov equation, and we can of course compute this by a few lines of code, but that's really that's the Lyapunov equation for computing K, or the K matrix is can be expressed by this Lyapunov equation. K matrix is equal to BB transpose plus A times K times A transpose. Okay, we'll talk about how to compute K from a state space representation by MATLAB, but or any programming language, doesn't really matter. Okay, so so what were we trying to do? We were trying to find a scaling transformation such that after we scale the state space representation and then compute the K matrix for the scaled state space representation, all the diagonal elements will be 1. So that's the purpose of scaling. The purpose of scaling, so-called scaling, is to scale the digital filter such that in the scaled state, if we take the expected value of the scaled state squared, that will be 1. So that's what we want to accomplish. We want to accomplish, the reason we are computing all this K is we want to make sure that K scaled, K value of the scaled matrix that we can compute from this original K will have 1 in all diagonal elements. Okay, so how do we define in the original equation, in the original scalar example, I tried to find out what I can multiply by so that we can guarantee the output to be bounded, either in L1 sense or in L2 sense. So the definition of scaling is xn or x scaled n, scaled state is equal to T inverse times xn. So if I take the original xn and then multiply by T inverse, so what we were trying to do is take the x and multiply by that scaled constant, which is, think of that constant as something T inverse, 1 by T, okay. Think of that as 1 by t. And then we get the scaled value. So another way to think about that is xn is equal to t times the scaled state. So T is an n by n matrix. T is an n by n matrix. So T is n by n matrix that is diagonal. Okay, so that means x1n is going to be T11 x scaled 1. Well, xin would be Tii times x scaled I. Okay, so how do I get the new state space representation? So to get new state space representation, we rewrite these two equations. xn is a t times scaled state. Okay, so xn is t times scaled state. So xn plus 1 t times xsn plus 1 is equal to a times xn plus b times un. Okay, so that is one equation. What's the other equation? Yn is C transpose xn plus dun. So Yn is equal to C transpose xn. Xn is this quantity t times x scaled plus d times un. Okay, so now in order to get the scaled state space, so how do we get the state space for the scaled system? So multiply by T inverse everywhere, T inverse. So multiply by T inverse. Okay, if I do that, then T inverse and T cancel out. And we have x scaled n plus 1 is equal to, I can call this whole thing as A of the scaled state space. A scaled x scaled state plus B scaled times un, and Y scaled, what will be Y scaled? So this is the C scaled transpose. C scaled transpose plus D is the same as a D scaled. D is the same as D scaled. So these are the parameters of the scaled state space. A scaled, B scaled, C scaled, D scaled. Okay, so once we have these things, then we want to make sure that K scaled so K scaled will be an identity matrix. So that's our goal. So the question we are asking is what should T be? What should this matrix T be such that the scaled, for the scaled state, the K matrix will be identity matrix. That means that not only, so if we satisfy that, not only are expected value of x s I squared equal to 1 for all I, but also all states are orthogonal. And why are we saying that? Well, if expected value of x2, x3, x scaled 2, x scaled 3 equal to 0, then x scaled 2 is orthogonal to x scaled 3. That's why their expected value is 0. So if we scale, after scaling, if we pick the right scale transformation TII, then after scaling, the K matrix will be an identity matrix, which means that all the state variables will be having expected value of this will be 1 in the square sense, mean square value will be 1. And that's really very important to us. Why is that important to us? Because in the original filter, it may be that if there are 3 states, the power of certain state may be 100. Power of another state may be just 3. Power of yet another state might be 10,000, for example. These are, of course, extreme examples. But the purpose of scaling is to bring them down, all of them to be same. And once I make them same, I can allocate the same word length to all the states. If something was 3, something was 100, something was 10,000, then we would need to allocate different number of integer bits to each and every state to be able to represent that expected value in square sense. So the purpose of scaling is to get a scaled state space so that the states are not only the states are orthogonal, but also they satisfy that the power of every state is same, and that helps us allocate same word length to each and every state. Okay, so what is expected value of x S transpose x scaled is going to be x scaled is T inverse xn. So that is going to be T inverse x times the transpose of that is going to be x transpose times T inverse. T is a diagonal matrix, don't worry about its transpose. Okay, T is a diagonal. So this is equal to T inverse expected value of x transpose times T inverse, which is equal to, so this is by definition K, this is the original state space K matrix, so that's K. So K of the scaled matrix, by the way, this is K of the scaled matrix is equal to T inverse times K times T inverse. Okay. Well, it should be T inverse transpose, but I am assuming T assumed to be diagonal. And you will quickly see that K scaled II, the diagonal value, will be, I am not writing this down, but you will quickly see that this is going to be KII divided by TII squared. TII squared. Well, if it was just scalar, then this would be 1 by T times K times 1 by T. And that means, this means for this to be equal to 1, choose TII, bring this to this side, is square root of KII. Okay, that completes the scaling. So now we are done. We are done with scaling. So the whole idea of scaling is to start with the state space representation of the filter, compute the K matrix, look at the diagonal elements, and then construct a transformation matrix T with the diagonal elements that are square root of KII, and then you will quickly see that the K scaled will be an identity matrix. Okay, so we have covered quite a bit of material. I think this is a good place to stop, and we will continue. We still have to talk about W matrix. just like we computed K to capture the effect of the state variables, the W is going to capture the roundup noise. And that means we need to compute the transfer function. So in order to compute K, we computed the transfer function from the input to the state. And in order to compute W, we need to compute the transfer function from X to the output. We need the transfer function from X to the output. And that's how we are going to compute the W matrix. So if you want to compute the Okay, so if we want to compute the transfer function from the input, from the state to the output, that's really, so I substitute u equal to 0. This edge goes away, b goes away, this edge goes away, and then we have some input. We want to compute the transfer function from this node to output, but keep that loop here. That loop cannot be ignored. Okay, so that's how we will compute the W matrix, and we'll do that next time. Okay, I will stop here. We will continue next time. Okay, so again I have your exam, so please don't go away. I will hand them out. And just like I think most of you have done well. Couple have done little worse than the first exam, and maybe 4 or 5 have done better than the first exam, but at the end we have 3 exams to add, and some have remained constant, some have remained steady. So